if m is the product of a bunch of other numbers, a bunch of other positive integers, where each of those other positive integers are pairwise relatively prime, GCD of ni and nj is 1 when I does not equal to j, then um is isomorphic to this external direct product of these U groups. Think about examples. For example, 105. What's the prime factorization of 105? 105 is 5 times 21, so it's also 3. It's 3 times 5 times 7. There are based on this corollary here, there are various ways of writing U105 as external direct products of other U groups. U7 with U15, because 7 and 15 multiplied to 105 and are relatively prime. U21 and U5, because 21 and 5 multiply to 105 and are relatively prime. Or if you want to factor 15 is 3 times 5 or 21 is 3 times 7, you can write it as this external direct product because 3, 5, and 7 are all pairwise relatively prime. How is that helpful? It's helpful because of another set of facts at the bottom of page 177 that's not labeled as a theorem, but maybe you want to write the word theorem in here in your book, theorem, because it's important and we will use it. Specific facts related to U groups of prime powers. U2, not the band, but U2, the group, it's so funny that we're still talking about U2 here in 2023 because U2 was famous back in the early 80s. They're still famous. I mean, even more extreme, the Rolling Stones and the Beatles were famous back in the 60s and they're still famous. Although most of the Beatles are dead now, right? Just Paul McCartney's alive. Everybody in the Rolling Stones is still alive, I think. Yeah. U2, though, everybody's alive in U2. It's a trivial group. It's isomorphic to 0. Wait a minute, shouldn't they write a 1 there? I mean, U2 doesn't have the element 0 in it. It's only got one element, 1. Right? Operations, multiplication. Okay, well, they're talking about U as being an additive group. Z1 effectively. 1 element, 0 under addition mod 1. Hardly ever call it Z1. Okay, but that's kind of what the author is thinking of when writing this. U4 is isomorphic to Z2. It's cyclic of order 2, right? Whatever its elements, 1 and 3 under multiplication mod 4. U2 to the n, where n is greater than or equal to 3, though, is isomorphic to this external direct product, which is not cyclic. So U8 is not cyclic. It's isomorphic if this is an 8 here, so that n is 3. This would be the external direct product of Z2 with itself. It'd be the Klein 4 group. U8 is isomorphic to the Klein 4 group, a non-cyclic group of order 4. If n is 4, so this is U16, this would be the external direct product of Z4 and Z2. Right? If n is 4, then n minus 2 is 2. 2 squared is 4. Z4 and Z2. If n is 5, so we're talking about U32. That would be Z8 with Z2. If n is 6, so we're talking about U64. Then it'd be Z16 with Z2. So powers of 2 are special because the powers of other primes are cyclic. Notice this is Z sub this entire one. This is in one entire subscript for Z. It's cyclic. So for example, if P is 3, U3, meaning U3 to the first power, and is 1, would be isomorphic to Z sub 3 to the first minus 3 to the 0. 3 minus 1, 2. U3 is isomorphic to Z2. Write these things down if you need to. Maybe I should. 3 is 3 to the first. So P is 3 and N is 1. This is isomorphic to Z sub 3 to the first minus 3 to the 0, according to this fact at the bottom of page 177. That's Z2. U9 is U of 3 squared, so now N is 2. That's isomorphic to Z sub, according to this fact, 3 squared minus 3 to the first. 9 minus 3, Z6. U of 27, which is U of 3 to the third. So now the N is 3, is isomorphic to Z sub 3 to the third minus 3 squared. Z sub 27 minus 9 is Z sub 18. So another example, now with a different prime, say U of 125. 125 is 5 to the third. That's the N. P is 5. This is isomorphic to Z sub 5 to the third minus 5 squared. Z sub 125 minus 25 is Z sub 100. U 125 is a cyclic group of order 100. This is worthwhile to be called the theorem, I think, even though the book doesn't do that. It's good to get lots of practice with these things. Thinking about examples, especially. Okay.